Good afternoon. My name is Patricia Johnson. This is my solution for radioactive decay. The rate of decay of a radioactive source falls from 3,000 counts per minute to 2,000 counts per minute 5 minutes later. From this information, determine the half-life of the substance. We begin solving this equation by recalling the formula for radioactive decay. The quantity of substance left at any time is equal to the original quantity times the exponential function raised to the power of k times t. K is the rate constant for this particular substance. T is the variable time. Let's write down what we know. We know the rate of decay is minus 3,000 counts per minute at time equals 0. We know that the rate of decay is minus 2,000 counts per minute at time equals 5. It's negative because this is a decay problem. We use the derivative of A with respect to t to denote the rate. By definition, at the half-life, we have 1/2 of the original quantity of substance remaining. We need to solve for the half-life, so let's make a table to summarize what we know. Here we have our formula, and we have specific values for the rate at certain points in time. Let's come up with an equation for the half-life. We can do this by substituting what we know into the equation for exponential decay. We divide by A0 on both sides, and this simplifies down to 1/2 equals the exponential function raised to the power of kt. We apply logarithmic function to both sides of the equation to extract th and solve for the half-life in terms of k. Now we need another equation. Here we are going to have to come up with an equation for the rate of decay, and we do this by taking the derivative of our radioactive decay equation. We must apply the rule of taking the derivative of an exponential function to simplify down this term to k times t to the exponential of kt. So here's our equation for the rate. Now we update our table and it looks like this. And we can start substituting what we know into our rate equation. So minus 3,000 will equal the original quantity times k times e raised to the 0 power, which is 1. So this simplifies down nicely. Substitute at 5 minutes, the rate is minus 2,000. And this simplifies, so we now have two equations with two variables. We have simultaneous equations, and we can solve for k in terms of A, then substitute it back into this equation to solve for A numerically. So let's do that. Again, we're applying logarithmic rules to simplify the exponential term. And we solve with our digital calculator that A0 equals 36,994.55. We substitute this back into our equation for k in terms of A, and we get this value for k. We substitute k back into our equation for half-life. Using our calculator, we get a half-life of 8.5475 minutes. This is greater than 0. It makes sense, but is the size making sense to me? I'm not sure. So let's take all our values that we calculated and substitute them back into the rate equation and see if we can calculate backwards our original rates. So here we have our value for A, K, and time at T0, and we calculate minus 3,000 counts. That makes sense. A and K at 5 minutes, and we calculate minus 2,000 counts per minute. That also makes sense. We can also validate our solution graphically. I like using Excel. So I create a table of values with time, rate is calculated, and our quantity of substance remaining. I check at 0, the rate is minus 3,000. At 5 minutes, it's minus 2,000. At around 8.5 minutes, which is our half-life, is around minus 5,000, 1,500. And this is illustrated in our graph here. Again, we could also use GeoGebra. In GeoGebra, I plot the function, which is the rate of decay. X is actually time. It comes out as this green line. And I plot two constants, time equal to 0 and time equal to 5, which come out as these vertical lines. And I observe the intercepts. 5 and minus 2,000 counts per minute. That makes sense. At 0 minutes, minus 3,000 counts per minute. That makes sense. So minus 2,000, minus 3,000. Thank you for listening.